Good morning, everyone, and welcome to today's Moldflow webinar. My name is Beth, and myself and Kristen are going to be presenting Understanding Warpage and Shrinkage in Moldflow Insight Part 2 today. So throughout today's presentation, please feel free to ask us questions as we have, again, myself and Kristen, as well as Paul and Jay, who are also on the Moldflow team behind the scenes and available to answer questions along the way. We'll also be posting this slide deck to the public folder shown here at autodesk.box.com /moldflow23. This webinar recording will also be posted to our YouTube channel afterwards. And again, there is the question box, so please feel free to ask us questions throughout the course of the webinar. So before discussing Understanding Warpage and Shrinkage in Moldflow Insight Part 2 today, I wanted to quickly inform you of the upcoming webinar we have scheduled, which will be on utilizing boundary conditions. Some of the past webinars we have done were on Understanding Warpage and Shrinkage Part 1 and Cooling Methods Part 1 and Part 2. If you're curious about any of these past webinars, you can visit our YouTube channel, which is the Autodesk Sim 360 page, and they will be listed under the Build Your Simulation IQ section. And again, if you receive this webinar from a colleague, you can always go to our forums or any other options shown here to sign up for yourself. The webinars will then be a series listed in your email, and you will be able to easily join the ones that you would like to attend. And now for a real brief summary for those of you who may not be familiar with our Autodesk Knowledge website. This is a website that the technical support specialists, such as myself and Kristen, create to publish articles based on topics and our troubleshooting efforts. We invite you to visit the Moldflow Insight troubleshooting article page shown here, as there are a list of all articles we have recently published. Listed here are some of our most recent Moldflow version releases. Moldflow 2017.3 is considered our most up-to-date version, and the download files for this version can be found under the Product Enhancements tab in your Autodesk account. And now to get into the content of today's webinar. I would first like to begin by providing a brief outline of the agenda we will cover today. First, I will begin by discussing the various warpage process settings available to you depending on if you're analyzing in dual domain, midplane, or 3D. Kristen will then review with you visualizing the warpage results as well as result interpretation. We'll then finish up by taking any questions you may have. So again, I'll begin today by discussing the different warpage process settings and inputs available to you depending on your molding process and the mesh type you have chosen. So the first mesh type I would like to discuss is dual domain. For each of the mesh types, page 2 of the process setting wizards is where you can modify the warp process settings. Of the 3 mesh types, I'd have to say dual domain has the least amount of user selection input options available to you. By design, a dual domain meshed model will always run a small deflection warpage analysis. This is the most common type of warp analysis and is the basis for both large deflection and buckling analyses, which we will discuss further when reviewing the warpage process setting options for midplane and 3D. With the small deflection analysis, there is a linear relationship between the applied load and the resulting deflection. As you can also see on this slide, you have the option for 3 additional selections. They are consider mold thermal expansion, isolate cause of warpage, and consider corner effects. By default, each of these options are turned off. You would want to select the consider mold thermal expansion if you want the warp or stress analysis to consider the effects of mold thermal expansion on the warpage or the molded in stress level in the part. You'd select isolate cause of warpage if you want the warp analysis to output the information about the dominant cause of warpage. And lastly, you would select corner effects if you want the warp analysis to calculate and account for deformations due to mold restraint-induced differential shrinkage. The other section available to you for selection is choosing a matrix solver. I want to note that choosing this matrix solver is an option for both dual domain and midplane meshes. This matrix solver is a technique used to solve the structural analysis matrix, and it optimizes for speed, efficiency, and RAM speed. By default, this matrix solver is set to automatic, which means that the analysis will automatically select a matrix solver appropriate to the size of your model. The other options you have available are the direct solver, the SSORCG solver, and the AMG solver, which are definitely mouthfuls there. Rarely will you have to use an option other than the default automatic, but more information can be found about each of these matrix solvers in our Autodesk Help Insight if you are interested. So next, I'd like to discuss the different options you have for warp process settings with a midplane meshed model. The first is selecting a warpage analysis type, of which there are 4 options, as you can see here. The first one I'd like to discuss is the small deflection analysis. You should select this analysis type if you know the warpage of the part is stable. Another option you have is a buckling analysis. You would want to choose this if you want the solver to identify whether the warpage is stable or unstable. If the part buckles, it's considered unstable, and if it does not buckle, it is considered stable. Please recognize that the buckling analysis does run a small deflection first. This small deflection then provides input to do the buckling portion. The onset of buckling is when the eigenvalue is below 1. Your third option here is a large deflection analysis, and you would want to select this analysis type if you expect the warpage of the part to be unstable and you want the most accurate prediction of the shape of the part. And lastly, you also have the automatic analysis option, and this is actually your default option. This warpage analysis type is only available for midplane meshes. You would keep this option selected if you want the solver to identify whether the warpage is stable or unstable. And this is actually done by first running a small deflection, then a buckling, then a large analysis if necessary. Please keep in mind that unless you have some prior expectation or knowledge of how your part is going to warp and if it's going to be stable or unstable, we do recommend that you just run the automatic analysis first on midplane models. The second thing you have to decide when setting up your analysis or your warpage analysis is which stress results to output. By default, it's set to none, but you do have the following stress results available to turn on if you do tell the solver to include them. They are, as you can see here, the principal residual stress, maximum shear stress, Mises Hankey stress, or you can choose to have the solver include all of these. Just keep in mind that for large models, the calculation of these additional stress results can require large amounts of CPU time, and results can take up large amounts of your disk space also. Next, you have some different options when considering if gate surface elements and cold runners should be factored into your warp analysis. The following 3 options are available to you, as you can see here. The first is exclude gate surface and cold runners, and you would want to select this if you do not want the gate surface or cold runner elements to be considered during the warp or stress analysis. This option is your best choice if you have not modeled them or if they are immediately removed after ejection. Your second option here is consider gate surface only, and this should be selected if the runners are removed after ejection, but the gate remains on your part. For this option, the simulation does consider the effect of the gate on the stresses or warpage in the part. Your final option here is consider gate, surface, and cold runners. And this option would be selected if the runners in the gate do happen to remain on your part after ejection, and you want the simulation to basically consider their effects on the stress or warpage in the part. I'd like you to keep in mind that in most cases, your cold runners and gates will be removed at ejection, so their effect on part stresses and warpage can normally be negated. And let's see. Okay, so lastly, I would like to discuss the warpage analysis types that are available for 3D meshed models. As you can see here, your options look similar to your midplane, except that you do not have an automatic option available to you with the 3D. The default warpage analysis type for 3D is small deflection, and just like with midplane, you would want to use this option if you expect the warpage of the part to be stable. What I'd also like to point out here is that with small deflection analyses, you have the option to select Use Mesh Aggregation, which is turned on by default. Using mesh aggregation assumes that the tetrahedral mesh of your part is only 2 elements thick. This will have a very minimal effect on the warp analysis and will improve solution speed and reduce memory requirements for your 3D analysis. So selecting mesh aggregation with a small deflection warp analysis also makes all of your tetrahedral elements second order by default. Tetrahedral second order elements take your typical 4 noded tetrahedral elements to a 10 noded tetrahedral element. This second order element is still considered is definitely considered a high quality element. And even 2 layers of second order tetrahedral elements can provide equally good deflection results for thin-walled parts. One thing I just wanted to quickly point out is not captured in this image is also the option to isolate the cause of warpage, but this is available to you with a small deflection 3D warpage analysis. The other 2 warpage analysis types that are available to you with 3D models are the large deflection analysis and the buckling analysis, which we did discuss when reviewing the midplane meshed models. Rarely will you run a large deflection or buckling analysis with 3D mesh models due to the types of geometries that are represented by the 3D meshed models. However, if you do decide to run either of these types in a 3D mesh, as you can see here, the option to use mesh aggregation is turned off and grayed out. And this is because this is not an option when running large deflection or buckling analyses, because your part is going to be solid or thick and true 3D. So this will cause your original mesh to be used for the analysis, and this can increase analysis time and memory requirements, but it does improve accuracy for true 3D parts. You'll also see that you have some different options available to you under Upgrade Tetrahedral Elements to second order with a large deflection analysis and buckling. By default, this is set to all, and you'll want to keep this option if you want the warpage solver to upgrade all elements in the part to second order for the most accurate results. This setting will, however, require the longest analysis time. You also have the automatic option, and you'll want to choose this if you want the warpage solver to automatically upgrade elements in the thin-walled areas of your part to second order to improve the accuracy of the results. Lastly, you have none, and if you'll want to use this if the part contains thin-walled areas, but you do not want second order elements to be used, either because you want the analysis to run as fast as possible, regardless of the loss in accuracy, or a previously attempted analysis using the automatic setting on a very large model failed due to insufficient system resources. The last item I want to discuss with you that is available to you with the 3D mesh type is choosing the number of threads for parallelization. You want You will most likely want to leave this option set to automatic, which is the default. With automatic, the solver automatically determines the most efficient number of threads to be used based on CPU usage. This is a good option if you want to take advantage of multi-core machines so that the analysis will run faster and split the job into multiple bits. So the million-dollar question is, should you use a 3D mesh or a dual domain mesh? And the answer is that there is no perfect answer for this question. When you know a warp analysis is going to be performed, special care should be taken to review the available material data. So when determining appropriate mesh type for a warp analysis, if CRIMS data is present, a dual domain mesh type will rely on this material information for the warpage calculation. 3D meshed models rely on PVT data, as well as the mechanical and coefficient of thermal expansion to calculate deflection. If your material only has CRIMS or only has mechanical and PVT data, this could be a good indication for which mesh type to possibly use. The tough decision is determining if your mesh can be properly represented with a dual domain model. And this can be done through reviewing mesh matching and if the thickness differences are properly captured by your dual domain mesh. What I also want to note on this slide is that when reviewing a material's properties, you may see that the mechanical properties of the material are in red. Red text is shown here. So values in red are representative of generic or supplemental data, and these values are based on the material family. When reviewing this material information, if supplemental data is used for the mechanical properties, but the material has good measured CRIMS, this is an example of a time to see if your model could be represented properly by a dual domain mesh. And with that, I am going to pass it over to Kristen, and she will next cover discussing visualizing warpage results.
Thanks, Beth. As Beth had mentioned, I'm going to talk a little bit more of the actual results behind it. So one of the first key things to understand would be the visualization tools within Moldflow, because sometimes those can be a little tough to interpret what exactly it's showing. So figured we'd dive into that right now. So speaking of the visualization tools, I'm really talking about within the results ribbon, there's a tab once you enable one of the deflection result plots. It'll basically say visualization, and within that there are a few additional options in there, such as best fit, anchors, scale, and so forth. So first I'm going to touch base on the best fit option. So whenever you first look at a deflection result, Synergy applies a best fit application of that deflection criteria. So using this to compare the geometry against your original part. Basically, as you can see in the photo there, or the screenshot, you can see kind of a shadow of the original part of that dustpan model, and then you see the deflection or deflected part, which is slightly offset from that original part, and that's where the automatic best fit option comes in. So basically what's happening is the solver is automatically assigning this default best fit by finding a location on that part that minimizes the deflection throughout the entire geometry. And this is usually within or near the centroid of the part. However, again, it depends on the geometry and how the part actually deforms, because it could be offset a little bit from that centroid point. Now, as I mentioned, it is a measurement of the before and after deflection. So if you use the query tool, you can see in this screenshot here, it pretty much spells out before and after. and gives you the coordinates of any points or places on that part that you select. And this can be helpful whenever you are comparing, what exactly is happening with that part. But again, since this is automatically calculated by the solvers, whenever you're actually comparing different studies, then this can be troublesome because it might not be measuring it from the exact same point on each of the different studies. And it also brings into line whenever you're comparing it to your actual molded parts after you've gone through and created the tooling and everything, then you could be measuring it differently than how Moldflow is kind of measuring that deflection. So this is just another example of that part. It's the same exact deflection result. I just kind of increased the scale factor. And you can see here where the entire part is kind of deforming inward towards the central location of that dustpan. And that's really where that best fit is kind of being measured off of at that point, because you can see it's all going towards that blue area. Now, whenever you're, say, wanting to compare it to other studies or else wanting to compare it to your molded parts, how will you do that? That's where anchor planes come in. So this is another visualization tool. It's something within Synergy, so you can apply it after you run the deflection simulation. You don't have to rerun the results afterwards, but basically all you're doing is constraining the orientation of your part to a specific plane. So I always think of it as kind of a fixture to orient that part in order to get the measurements that you're looking for. So if you have tolerances or dimensions that you're looking to compare to, say, critical dimensions on the part drawings, then you can use this anchor plane to help to orient that correctly for you. Now in those pictures there, I basically am just showing the 3 steps to assigning that anchor plane. So whenever you go to add an anchor plane, it asks for nodes to select. And within those nodes, it's basically 3 separate nodes. The first one is a point to match the point on the original part. So you select it somewhere where you want to measure off of. And then the second point is created to create a line between those two. So if you have a critical dimension, say, on an edge of a part, then try to align it that way, because then it'll orient the deflected part to that direction as well. The third point then creates kind of a plane so that you can measure off of that point for other measurements also. And it just kind of constrains it loosely there, just, again, orientation-wise. And again, Synergy applies an automatic anchor plane to this, and it kind of plays along with that best fit option. So you most likely need to set a custom plane for your particular part or study, and adding several anchor planes allows for you to switch between the different measurements, so you can maybe add different planes to each of the different critical dimensions on your part and easily filter through those. So circling back to that same dustpan part, you remember it was kind of deflecting inward on that original part. Now if we assign an anchor plane to where the X, Y are located up there, let me just point that out for you. So basically we did the first point on this corner here, and then second point down here, or I'm sorry, second point here, and then third point here, to essentially create a plane on that surface. And from there, the part is basically being measured off of that for the deflection results. So you can see here with the scale factor increased significantly. I think I used about 50 on this. Looking at, say, just this line, the edge of the part is going kind of upward towards that anchor plane to be measured off of it. It's not changing the actual values or deflection of that part. It's just changing the reference, the orientation of how it's being measured there. Now moving on to the other visualization tools. As I mentioned, the scale option that I used in that last result, you can change this around as much as you want. It's essentially there to make it easier to interpret what direction the results might be going. So you can see in the example listed below there, I have a scale factor of 1 on the dustpan on the left-hand side, whereas on the right hand, there's a scale factor of 10. And it's really just showing that, hey, there might be some issues with it deflecting inward near the handle there and could potentially not get a flat part there. Now looking at the other options within the visualization tools, the translation option, this is there to either translate or rotate the warpage in a negative or positive direction. Really not too many people see a use or see a need to use this option. However, it's there if you need to. And then the display option essentially allows you to turn on and off, say, that shadow of the original part, or else turn on or off the visibility of the anchor plane. So if we circle back to the previous part here, or screenshot, if we enabled the anchor plane to actually be seen, then the spot where I was pointing previously, so right here, you would see kind of a faint outline of the actual plane on there. And that's something, if we have some time at the end of this, I can switch over to my my Synergy instance and we can take a look at that together. So moving forward, there's a second place where you can actually customize these deflection plots. And this is actually located in the plot properties. So again, once you have that result enabled or visible on your screen, then you would be able to go into those plot properties for that result and switch over to the deflection plots tab. And there you can see a few more options to customize it. So the first one here is I just showcased the option to be able to switch between a traditional Cartesian coordinate system versus a cylindrical coordinate system. And that's basically whenever you have a, say, a round part that you're really looking for how out of center it might be or things like that. This can help to better interpret those results. So you can see once you switch it over to the cylindrical, you get a different option for, say, the magnitude component. There's the, oops, sorry about that. There's the radial component as well as, not shown here, the axial component. And it'll also keep the Z component there as well. And for each of the deflection results, or you can create new deflection results and apply these to that, you're able to switch between those to be able to better interpret that cylindrical component. And you can see the results also show this once you switch it over to, say, the radial component. Instead of showing or naming the result deflection all effects X component, for example, this switches that particular plot to the R component. So it's easy to circle back and take a look at that exactly. So that's nice whenever you're doing a lot of comparisons. Again, if you, say, have a single component on your part that is cylindrical and you're curious about how that would be with regards to deflection, but you still want to be able to switch back and forth between this radial result as well as the original Cartesian deflection results. That's where you can right-click on the warp folder there and be able to add a new plot with that deflection and have two different plots going at the same time, so you don't have to keep switching those plot properties. The second option within that plot properties for the deflection results specifically is shrinkage compensation. So this is a big topic. I kind of narrowed it down just to for ease of the presentation, but there's a lot of good information on this if you're curious about it within the help documents, as well as help articles that Beth had showcased earlier on the Autodesk Knowledge Network. But essentially, the shrinkage compensation is a way to increase the cavity size to account for any estimated material shrinkage. You can do this isotropically and isotropically, and it also allows for an automatic calculation behind these, as well as a manual input on these shrinkage values. So if you have experience with, say, how a specific part shrinks, then you can enter those in by yourself. Or if you're not too sure about it, you can have Moldflow kind of calculate it based on the results of that deflection analysis. And as for visualization tools, I did want to just briefly showcase that Tim Benast and Jay Shoemaker, both Autodesk employees here, Jay's here in the background helping us out. Thanks, Jay. They actually presented an AU presentation on this particular topic. So if you're not sure exactly how to utilize those tools for measuring, say, your critical dimensions compared to how your 2D drawing shows, then take a look at this presentation because it's definitely an eye-opener and very neat way to present the information. They go through and showcase incorrect versus correct methods for measuring certain items such as flatness, parallelism, and straightness. So very neat presentation to take a look at. And what you would just have to do is sign in using your Autodesk account login, and you'll be able to access, I think this one was recorded live, as well as the slide deck and handouts that go with it. So moving forward into actually interpreting the results. So whenever you're looking at a deflection result, whether it be a traditional, say, all effects result, or maybe a more complex one, say the modal shape result, you want to ask yourself a couple questions. Mainly, are the magnitudes roughly what you expected from it? And then also, does the pattern look sensible? Given the geometry, should it be warping like that? Are the ribs or thickness changes, or maybe the flow pattern, making sense with the way that the part is deflecting there? And then also, are any symmetries being reproduced? So this is not necessarily talking about cavities, but if you're working on a single part where, say, it's got 4 identical geometries in there somewhere, then are they all acting the same, or is one acting maybe a little bit differently, and what could be the cause of that? And another key idea to keep in mind is, after looking at the initial deflection results that you run, you want to keep in mind to understand that there could be a need to circle back and run another analysis with a finer mesh, because the finer mesh might be able to better capture that deflection in there. And as Beth had mentioned, it also plays on the mesh actually capturing that geometry as well. So you can see on the left there's a much coarser mesh than on the right, bottom right there, and that could potentially cause some trouble for being able to see exactly what's happening with regards to why a part might be deflecting a certain way. So adding some refinement, maybe not as much as I did in this screenshot here, but it could help to better make things a little bit clearer for you. So this slide right here, pretty straightforward. Whenever you're looking at the actual deflection results, these help to estimate what the part shape will be like once it's actually molded. using the other result plots can help to give you clues and build for why it might be shaped like that. So we'll go into that a little bit in the next slide here. And I know Beth had mentioned briefly the isolate cause of warpage setting. However, once you do get the actual results behind it, you essentially get 3 different plots behind it. The first is the differential cooling, and for this, you can essentially utilize additional result plots to further investigate this. So looking into part temperature, mold temperature results, excuse me, they can help to identify where additional cooling or change of cooling channels might be needed to circle back and test run. The next one is the differential shrinkage. So this one can be reviewed or reduced by altering the pack pressure, reducing part thickness variations, and possibly adding a mold insert, essentially with the idea to pull more heat out of the tool in a more uniform manner. So again, it's very similar to the differential cooling aspect of it. However, here you can use result plots such as, say, pressure and average temperature, or average volumetric shrinkage result to help with that. And when you're looking at the volumetric shrinkage result, this result, a lot of individuals come to us on the support team asking, how do I really interpret these? And that for that one, you're really looking for a large difference between how the part's shrinking. So if you look at the average volumetric shrinkage result and notice that, say, it's jumping from, 4% shrinkage in one section versus, say, 10% in another region right next to it, then there could be potential for either deflection or surface defects in there. And the last option that the isolate cause of warpage shows is the orientation effects. And for this one, orientation is pretty straightforward. It's the orientation of that flow. So how's the material flowing and how is that affecting the deflected part, or how the part deflects? So this can be minimized by changing process settings, changing the gating location, or modifying the part geometry. And the other option that Beth had mentioned is the consider corner effects. And that one, again, shows its own result in there that you can get a feel for what the influence of corner effects are towards the overall deflection of the part. And for that one, again, it's really coming down to the part and mold temperatures to see how that is acting thermally against that area of the part. Now, for the stress analysis, Beth described a few details on how it's actually run. Now, whenever you're looking at the results, as you can see here, they are spread between the different mesh types. So for, say, the first and second principal direction plots, these are used for more brittle materials to find high stress areas to compare with your material data. And they're plotted across a section of the part. So instead of being similar to the overall part, you're kind of taking a cross section of it and looking at the stress between that cross section. When you're looking into more ductile materials, the Mises-Henke option or result is often looked at. And you can identify high stress areas in the deformed state after ejection. Now, in some occasions you might see this value as negative, which ultimately it should be positive. However, if it is negative, it's usually a very, very small number there. So that's typically assumed as 0 at that point. And the final one, there are a couple results for it, but it's the von Mises stress result. And this one essentially is looking at the core that you're using. So you would get it if you're running a paddle shift or a core warpage analysis on your core. And it pretty much shows, whenever you're using a ductile material, high stress areas that could result in fatigue on the mold and ultimately cause core cracking. So it can potentially save you from having to cause unneeded stress on that core. And moving forward to the buckle analysis. So this one, again, it's a separate warpage analysis that you have to run. And since it does go on to calculate what's called as a eigenvalue, this is where you want to both look in the log file as well as what results it entails, as this can help to identify the failure of the part. And again, as Beth mentioned, if it is less than 1, then there could be a failure, because essentially I like to think of it kind of as a factor of safety in there. If you're applying one load in there, then that's going to be 100% of the load. If you increase it, or if you say have a value of, I don't know, let's say 3 or 4, then you would be doing about 300 or 400% of the load in that particular area of the tool or part. So the result kind of entails the same thing there. You can see there is 100%. So the scale here is showing more percentage rather than actual values, and that's where the percentage comes in hand, where you can see, okay, so 100% looks good there. Might need some additional structural stability in the lower percentage areas to help gain the stronger part. So with that, I did want to bring up a quick poll, because with warpage it is such a large topic that we weren't quite sure exactly what direction we were going here. So hopefully this presentation was able to give you a few new insights into how to interpret your warpage, as well as understanding how to actually run it. So what we're going to do is just launch this poll for you, and it's actually based on the DOE analysis. So here is the poll here. Have you used a DOE or parametric study to minimize your warpage? I know in the 2017.3 version, this one has added a few new features in here that make it a lot easier to help reduce your workload and to do it all in one in that DOE or parametric study. So this was essentially to help see if we need to pull this out into its own topic here to cover. I'll leave it open for just another moment here, see if we can get some more votes here. All right, looks like most of you haven't even seen that before, so great. Okay, let me go ahead and close that and show you the results there. So you can see here that a couple of you have tried this out and love it. Seems like it's working out great for you. A few have either set it up but not sure what to really look at in it, or might not be sure if they've set it up correctly. And then a few also have not needed to use it yet. And then a good number, 39%, have indicated that you're curious about learning more. So what we might do is incorporate this into one of our future webinars and see if we can pull it out into its own topic, or maybe circle it into maybe different features of the DOE and parametric studies to help to better understand those. So with that, I'm going to go ahead and open the floor to questions. I don't know, Beth, have any good ones come in here? Well, they're all good questions. Sorry, worded wrong.
Sure. So let's see. We've been working to kind of answer some of them along the way. Let's see. So what type of mesh will give you the best prediction for warpage values, considering the part is large and thin?
So that kind of circles around to what Beth was describing a little bit earlier. It's really tough to get a yes or no answer for these types of, or when considering what type of mesh to use for your part, because it's not cookie cutters. We're not all using the same parts here. So whenever you're looking at a very thin part, if it's super thin, you might consider either midplane or dual domain. But again, once you get into more complex geometry, that might not be able to capture it the best. So you might have to ultimately turn it over to the 3D mesh to be able to accurately get a good feel for it within the solvers. And again, that does circle back over to the material data as well. If you're trusting of the material data to be for the midplane or dual domain analysis, then that could have an effect on maybe swaying your answer one way versus another. But again, it might not be as clear-cut as you'd hoped. So, good question. Oh,
Kristen,
go ahead,
can
Jay.
I add a couple of things? Yeah, everything you said is right on the money, but I would maybe add a couple of more things. When I hear large and thin, one of the things that pops into my mind is the possibility of buckling. And it really boils down to two things if a part is going to buckle. Is the part structurally quite sound, or is it structurally not very strong? Flat plate. Think of an extruded sheet is the most unstable shape. As soon as you add sides, ribs, and other things, it becomes structurally strong. So, that is one consideration, and that would then lead towards considering midplane as the mesh type you'd want to use, because we can determine that onset of buckling. Another factor would be, what is the material that you're using? If you're using a glass reinforced polymer, nylon, ABS, polycarbonate, propylene, something like that, it is very unlikely to buckle, even if the structure is rather weak because of the modulus of the material. But if you have a rather low modulus material, such as low density polyethylene, maybe even a high density polyethylene, and a rather weak structure, the part is going to tend to buckle. So that adds, unfortunately, to the complexity of the problem. And as I believe Kristen mentioned, the quality of the material data is also very important, in that the better the quality of the material data, of course you'll get better predictions.
Yep, exactly, Jay. Thanks for cutting in there. Yeah, we really try to make the product very user-friendly, but there are some things that are, again, tough to interpret yes or no on that, so hopefully that clears it up a little bit. So it looks like we're getting a lot of questions in here. A few of them may have been covered by what Jay and I were just talking about there. Let's see, what else could we check in here? Beth, you want to go ahead and?
Sure. So I do see one question here. Looks like someone has a situation using the 3D mesh where coarser mesh over predicted warp by about 5 times. So I think this circles back to what Kristen spoke about, needing to review the quality of your mesh, and if you are identifying it as a more coarse mesh, and with the finer mesh you're getting more accurate warpage results. I wouldn't really compare one mesh type to the other. I would go with your finer meshed value there. Anything to add to that, Kristen?
Yeah, I'd say that's definitely the first place that we would start as if say we got a support case in where someone was coming to us saying their parts had way too much deflection or warpage in there. We'd almost start working backwards and make sure our process settings match to from the molded part to the simulation. As well as just the general setup of it. If you have the cooling line set up, incorporate that into the simulation as well as feed system, and make sure gate sizes are correct and things like that. And then from there, it's more of trying to investigate those other results to see if there might be any outliers in there, if the pressure's matching up correctly, and so forth, to try to pinpoint why that might be. Good question.
All right, great. Thank you, Kristen. So another question here. Do resins most commonly have CRIMS or mechanical PBT data? Is one more standard than the other? Can the material quality indicator be a quick reference to know if the resin has CRIMS or mechanical PBT? So if the material is going to have CRIMS or not, that would depend on if it was data fitted for it. And it's pretty easy to go I'd say most likely if you're looking at a gold material across the board for fill, pack, and warp, that it most likely does have the CRIMS, but that may not always be the case. So you can go into the material properties and take a look under the shrinkage tab, and that'll tell you if you have the CRIMS data in there or not. So I wouldn't just bank on if it's showing as gold, but I would also go in and take a look at the actual material properties themselves.
Yeah, and just to add to that, if, say, you're really looking for that CRIMS data in there, if you know you're going to be working with the dual domain mesh on your part, talk to our plastics lab, see what their opinion is, if it could be best to get it tested for that CRIMS data, as they do that very frequently, test it for certain materials in order to add those additional values in there. All right, and there's a couple questions here. So a few related to scripts behind measuring, say, cylindricity in there. I do know there are scripts out there available for it. I would say check the forums for that, because either the forums or the Autodesk Knowledge Network, to see if there are the scripts up there, posted up there. If not, for any scripting, definitely post something new to the forums, because it really generates. We have a really good community on the forums. I'm sure most of you have at least dabbled in the forums a little bit. But if, say, no other users are able to help out there, our developers are also on there. I'm on there. Beth's on there. Jay's on there every once in a while, too. So we're all there to help out. It's very much a community. And I do see a couple questions here, again, more related to measuring actual dimensions in your part specifically. Again, I'd circle back to the AU presentation I brought up. I'm sure Jay might be able to shed a little bit more light on. Let me see if I can find that question there.
Yeah, I think I already read it. The one I'm thinking of is you're interested in distance between nodes, and you want to track it from one study to another. There's a couple of ways that you could do it, depending on what your situation is. Probably the easiest one is a little manual, but it's still pretty quick, is on your first study, identify the very specific nodes that are of interest to you for a particular dimension, say node 501 and 45. You know, just pick two numbers out of the year, and then copy and paste those two nodes into your study notes. And so you will have them there, and then identify them. This is for critical dimension 1 or something. And then when you're on to your second study, most likely you duplicated it from the first study. Those plot notes would be there. So there we've got two nodes, 104 and 105. Look at that. They're even neighbors. When you go on to the next one, the second study, you've got in your plot notes the list of notes, and you can copy and paste it back into the Examine tool. And that way you have it. So that is probably the easiest thing to do. If in fact you're running a DOE, you can set up a critical dimension, and that would get tracked from study to study as well. And then, of course, because it's a DOE, you can see the influence of those dimensions on parameters that you've changed. So that kind of kills two birds with one stone, if you will. Does two things at the same time. So I really like the DOE for that, for setting up critical dimensions. Those would probably be the easiest two ways to do it.
Yeah, and that brings up a good point, Jay. The DOE, the poll question that we threw out there for everyone, we could certainly incorporate that into one of the future webinars as well, to take a closer look at that.
One of the things I did in the past in conjunction with some of my students at Western Michigan University is look at that exact same thing. We used the DOE analysis in critical dimensions and looked at processing parameters relative to dimensional tolerances on those dimensions, and how we changed the process. Were we able to always meet those critical dimensions, or would a typical variation in processing parameters go outside that tolerance? So that is something that is pretty easily done with the DOE, and I think it potentially adds a lot of value to our simulations by doing that what if. Okay, we've got our part warpage says it's good, check critical dimensions are good, but how stable is that over ranges of processing conditions you might see on the production floor?
Great, thanks. So we are at the 12 o'clock time limit here. So what we'll do is, it looks like we've answered probably most of the questions here. However, if we didn't answer your question, please go ahead onto the forums and post it on there, because we'll take a look through those, and that way we can help answer you, or some of the other users can help answer those too. So thanks again for joining us today. We look forward to seeing you at the next one. Have a great rest of your week.